Before we look at manually driving some destruction deformation, we're going to make a couple changes to our Voronoi setup, and we're also going to bundle it up as a Houdini digital asset, or HDA. Another term you may have heard is OTL, which is more or less synonymous with HDA for our purposes. So if you go to the subnet where you've created your fracture setup, I've renamed mine Voronoi Cutters. You can right-click on that and click Create Digital Asset. It'll prompt you for a name, which is the name of the node, of course. I'll just leave mine named Voronoi Cutters. For the operator label, I'll give it a slightly nicer name, Voronoi space Cutters, both capitalized. And you'll see that this will default to saving this asset, and I'm on Windows, so it'll be in my user documents Houdini file, OTLs, which is previously more common use terminology rather than HDA. And the file will be Voronoi Cutters.hdanc. NC because we're using a non-commercial version of Houdini for this. So if we accept this, you'll see that it gives us some options to set up some of the parameters and other details of our Houdini digital assets. The key thing of importance here is to set up all the parameters we might need for our fracture. So if you click on parameters, you'll see a list of all the various parameter types available, whether it's numeric types like floats and integers, vectors. You have files and strings and any parameter type that you would want. Hopefully, while working on this fracture setup, you've gotten a sense for which parameters are the key ones that you'll need to adjust for different scenarios or for different results to fine-tune the look that you're going for. Some key ones are the number of scatter points, the distance that we're going to be calling points around the cutter geometry, and so on and so forth. So let's start by looking into the network itself to identify some of these key parameters here. And we don't have to identify every single parameter that we'll need to use in every single scenario in the future for other projects. We can start by the main ones that we know we need to tweak in this scene, and down the road, as you use this for other projects, you can continue to add extra options as you see fit for things like different scene scale and that sort of thing. So tracing from our input of our fracture setup, we have our VDB from polygons. For different scales, you'll probably need to change the voxel size, and similar the VDB from particles voxel size. Those will need some tweaking. The point radius scale, all of these sorts of things will need to tweak. Well, you will need to tweak for different size scenes. But for this scene, we'll leave it alone, since we don't want to overcomplicate our HDA to start with. We'll just do the most important stuff first. If we trace through a little further, we'll get to one of our scatter nodes, which, as you may have found, is one of the main points of tweaking our Voronoi look and stability. So this count is an important one to have control over. So let's create a float attribute as a multiplier on our point count. So if you drag a float parameter from this left pane to the right pane here, we can give it a name. And I'm going to call this large chunks resolution. We can also use the same thing as the label, except we'll capitalize it and put in spaces to make it a little bit more readable. Now let's also create an attribute for the scatter points along the cutter planes. So for that, we'll drop in another float parameter, and we'll call this cutter points resolution. And once again, we'll use the same term as a label with caps and spacing. Now if we go down to the attribute transfer, this is another area that we'll want some more control over, particularly the distance that we're deleting points away from the cutter planes. So right now, we're deleting all of the large chunk points within 4 units of the cutter planes. We could very likely want to tweak that to make the cutting areas much smaller and more well defined, or a little bit larger and a little bit more stable to ensure that it always makes a cut and that large chunks don't get joined together. So for that, we'll drop in another float parameter and call this cutter distance. And then we'll move on to our final scatter node. This is the scatter node that we're using to create our clusters along the cutter planes. It's this scatter node here. Now, since each of these scatter points represents a discrete cluster value and a discrete clustered chunk along those cutter planes, I'm thinking it would make sense for the parameter to be the exact number here rather than a multiplier on a resolution. So let's use an integer attribute for this one, since we can't have a decimal or fractional number of points here, and we'll call this cutter chunks. Now that we've covered our scatters and our main attribute transfer, let's go down to the Voronoi fracture node itself, and we'll look at some of the attributes that the Voronoi fracture node is kicking out after it does the fracture. So if you click on attributes, you'll see a name prefix setting, which is a string that represents the prefix on every piece. So you'll have piece 1, piece 2, 3, or however many fracture pieces that this kicks out. So this will often want to give a more intuitive name, and we'll create a string parameter on our HDA, and we'll use this to control the prefix of every piece, so we'll simply call this piece prefix. Now you may find as you use this fracture setup for other pieces of geometry or in other scenes that you'll need to change some other settings, but this will be a good starting point for the main ones that we'll need to change for the different pieces in our scene. Now I'm going to reorganize this a little bit and place our piece prefix as the first parameter, since it makes sense to me for the first one to be the name of the chunk of geometry we're dealing with. And then I think the cutter distance and then cutter chunks make sense next, and chunks resolution afterwards. It's kind of up to your own judgment how you arrange these things, but this seems pretty intuitive to start with. And now we can start setting some of the default values on our parameters. I've cranked up my settings a bit since our last week's sessions, so we may want to have the defaults be some slightly lower settings than I have in my current scene, because you don't want this to be super heavy to process as soon as you or another user creates it in the scene. So if you click on channels in the parameter description here, you notice that there's a default value here that we can use to specify the default for each parameter. For our piece prefix, I'm just going to use piece underscore as our default value. And for the cutter distance, we can use the same distance that we're currently using in our attribute transfer. That seems reasonable enough for now. We'll set the cutter distance to 4. For cutter chunks, let's go take a look at the value in the scatter node here. Right now I'm using 15 times 100, so 1500, but let's start with 1000. Now for the cutter points resolution, I'm actually thinking that instead of a multiplier, let's use a literal value for the force total count points that we're scattering along the planes. So if we go back to the parameter tab, we can change the type here from float to integer, since we can't scatter a fractional number of points. And right now we're scattering 6 times 8,000, which is a pretty high number, but we'll default to a value of 10,000. Now for the large chunks resolution, let's also make that an integer, which will be the literal number of scattered points to keep things consistent with how we're controlling the cutter points. And let's look at the value we have right now. And we're currently scattering 2 times 20,000 points. So let's do something much lower. We'll use the same default for the large chunks as we are with the cutter points. So let's default it to 10,000, but we'll know that for our case we'll have to increase that right away. Now if we accept the changes to our HDA parameters here, you'll not see anything different right away, but if we go up a level and look at our Voronoi Cutters node, you'll notice that this has all of the parameters that we've set up with all of the defaults that we've set up. And if you tab in the node network here and start typing Voronoi, you'll see our Voronoi Cutters HDA automatically pop up as a node that we can drop in our scene. And if you create a new one, you'll see that it has all of those same settings that we would expect as the defaults. But right now, these settings are not connected to the actual parameters they're controlling. In order to connect these to the underlying parameter, we're going to attach them one by right-clicking on the parameter and then copy parameter. And then let's dive back into our network and go to the node that that parameter is driving. In this case, we've copied piece prefix, and that's driving name prefix here. So you can right-click in that parameter and then select Paste Copied Relative References. So what this does is this creates a channel reference to the Voronoi Cutters node and the specific parameter that we've copied. Now let's do the same for all of our other parameters, starting with the cutter distance. We'll copy that and then go to our attribute transfer node, and that's going to be the distance threshold of that attribute transfer. Then we'll copy the cutter chunks, and that will be the number of points that are scattered, and these scatter points that represent all of the cluster values that are being transferred onto the cutters. So we'll paste copied relative references there as well. And you can verify that this is working by clicking on the name of force total count. That'll toggle between the current value that it finds and the channel reference that it's pointing to. So it's pointing to the cutter chunks parameter and getting a value of 1000 that we've specified up there. Then we'll copy the cutter points resolution, and we'll paste that onto the scatter node for our cutter geometry. And finally, we'll copy our large chunks resolution, and we'll paste that parameter into the scatter points for the large chunk scatter node. Now, all of these changes we've been making to link these parameters aren't saved to the master HDA file that we originally created when we created our digital asset. So if you create a new Voronoi Cutters node, we'll tab and drop a new Voronoi Cutters here. You'll notice if you dive inside there and select, for example, the Voronoi Fracture node, this name prefix is no longer, this isn't getting the parameter reference that we created on our master copy here. So the way to save the changes we make, in this case those parameter links, you would right click on the node. Actually, let me expand my node network a little bit so you can see this more easily. If you right click here and click Save Node Type, that will save all the changes we made to the master definition for that HDA. So now when you dive inside this Voronoi Cutters here and select this Voronoi Fracture node, you'll see that this is automatically updated to the latest definition for this asset with all the parameter references, like this name prefix here, which is now correctly referencing the driving parameter. Now we're going to make just a couple more changes to our fracture setup here, so we can delete this extra copy of the Voronoi Cutters node that we created and dive back into the fracture setup. Now I've created a file node here where I've cached out the results of my fracture, just so that we can easily work on this without recooking anything. And let's take a look at the exploded view for that fracture. You'll notice that I've added in a lot more detail than we were getting last week. Obviously a lot more cutter geometry specified and a lot more detail in each piece. If we hop up a level, you can see all of the cutter geometry that I've used to create these pieces. And I've set these cutter geometries up with our artistic goals in mind. Specifically, I was imagining this whole area as a chunk that will be cut away from the helipad, already gone at the beginning of the shot, and I figured we'd have a big hole here, and I made sure to have a nice fairly even gash along the center of this where it splits in half, and a lot more fracturing much more densely around where the character's impact is, with some crack lines emanating from the impact point. And if we go back to our exploded view down here, all of this increase in detail that you see was largely accomplished by increasing the number of scatter points to help make sure that all of these large chunks didn't connect to each other, that we had a good solid break between them, and to increase the nice shapes along all of these edges here, and to make sure that you avoid the kind of low-res geometric classic Voronoi shape. Now let's take a look at some of the geometry that the fracture is creating. If you look closely at some of these pieces, for example, let's take this primitive right here. You'll notice it has more than 4 sides to it. Looks like 1, 2, 3, 4, 5, 6, probably 7 sides to it. And generally speaking, it's bad practice to have geometry with more than 4 sides to it. So I always make sure to drop a divide node after the fracture and set the maximum edges to 4. So this will ensure that all of our primitives have no more than 4 sides. So obviously this will create a lot more geometry to ensure that none of them are any more than 4 sides. That'll be much better and cleaner geometry to deal with, especially if we pass it down the pipeline to, any renderer that we may be using. Another extremely helpful thing to add to any fracture setup is an attribute for the volume of each chunk. Oftentimes we'll want to delete out the tiny little pieces, or we may want to set simulation attributes differently for the little pieces versus the big ones. For example, maybe the initial velocities would be different for the small versus large chunks. That sort of thing. Could be any number of differences in the way we treat them, but we'll want to store an attribute on each chunk for that volume. So in order to do that, we'll use a for each loop to operate on each chunk individually. So if you type in for each in your node network here, it'll automatically create a for each begin and a for each end node. These new for each nodes in Houdini are a lot easier to use than the old ones, in my opinion. It's a lot more clear what's happening, and it's quite a nice little upgrade. And this will be very helpful to iterate over each chunk. So if you click on the end node, you'll see that it's defaulting to using an attribute called name to define each piece to treat separately in a loop here. Now this default attribute of name will actually work okay for us, because if we look at the spreadsheet on our fracture, you'll see that we already have a unique name on each piece. So this is it's the right attribute to use for iterations. Now within this for each loop, we can create a measure node, which is useful for measuring a few different properties. It'll default to the perimeter of the primitive. It can also do area, curvature, volume. In our case, we want volume. Now if we look at the spreadsheet for our end results, you'll notice we now have a primitive attribute called volume, but this has a lot of crazy values in it. We're seeing ranging from minus 493,000 all the way through these enormous numbers. This is 155,000, and this is because by default this measure node measures the volume of each primitive based on the primitive face and a point specified by center here. So right now it's measuring the volume between each primitive and the origin at 0, 0, 0. So what we want to do is measure the volume to the centroid of each piece that we're analyzing. So in order to do that, we'll start by creating a null node in our for each loop, and we'll call this piece input. Then if you go back to the measure node, we can reference this piece input to find its centroid. We have a convenient function simply called centroid, which takes two parameters. The first one will be a string pathed to another geometry node in the scene. In this case, we'll type in ... which will reference the parent node, Voronoi cutters. And within Voronoi cutters, we're going to reference the piece input null. You'll notice that this, as soon as we start typing it, it'll automatically find that node here. So you can click on that and use that as the node that we are referencing the centroid of. And for this float attribute, you specify either d_x or d_y or d_z, which will tell it to fetch either the xyz value of that centroid. So for the first center parameter here, we want the x value. And we can copy this whole expression, and then in the second value of center, we'll look up the y value instead. And the third, we'll look up the z value. So now, when our for each loop recooks, you'll notice that we have much more reasonable values for the sizes of our volume. Now, it's not very useful to have the volume of each primitive individually. What we really want is the volume of the entire chunk, so that we can, for example, delete the tiny pieces or set attributes differently on the large versus small ones. For example, we may set our initial velocities different depending on how big the pieces are. So Houdini offers us an easy way to add up all of the volume primitive attributes and store that on the entire piece. So if we create an attribute promote node and wire that in after the for each, we're going to use this to promote our primitive volume attribute to a detail attribute. So the original class will be primitive, and this drop-down shows all of our primitive attributes now, so we want volume. And we'll promote that to a detail attribute. And the promotion method here will be sum, so that it adds up all of the primitive attributes. We don't need to change the name, and we will delete the original attribute, because those individual primitive volumes are useless to us. So let's display the attribute promote and look at the spreadsheet for it. So you'll notice there's no longer a primitive attribute called volume. Instead, we have a detail attribute with a single volume for the entire piece. If you're not familiar with detail attributes, the difference is that all of the geometry has an attribute, for individual points or individual vertices or primitives, but detail attributes are one attribute on the whole of the geometry. It's not per component. So this is useful for storing a sum of all the values, but right now it's storing a sum of the volumes of all of the pieces all put together. But we really want this per piece, so we're going to do this within our for loop. Now if we put our display flag back on the for each node, I'm going to set my update to manual so it doesn't recook every time I change the loop. But we're going to put this attribute promote in after the measure node. So what this will do is for every single piece that this loop iterates on, it'll take all the primitives and store that in the detail attribute just for that one piece, and then we can use another attribute promote node to push that summed value down to all the primitives once again. So if we create another attribute promote node, we'll do the exact reverse of what we just did. We will set the original class to detail, and this list will not auto-update because we're set to manual updating, not automatic, but we know it's called volume, so we can type that in, and we're going to push that back down to the primitive attributes. Average is just fine because the detail is just one value, so whether we have the method set to average, max, min, sum, whatever, it'll work the same to push it back down. So now once we recook this for each node, we can pull the spreadsheet back up. You'll notice there's no longer a detail attribute called volume. But when you go to the primitives, and let's sort these primitives by name, you'll notice that all of the primitives for each piece have the same volume attribute. Piece 0 is 100.88, piece 149 is 826, and so on and so forth. So each piece here has the entire volume of that piece as a whole. And this is much more useful information than all of the individual primitives having their own volume attribute. So let's take a look at actually using that volume attribute quickly. Let's drop in a BLAST node and connect the for each to that. And in this group, we're going to type @volume for the volume attribute is less than 20. We're going to specify this group type as a primitive group and delete non-selected so that it deletes everything that is above 20 instead of below it. You'll notice this only isolates some of the smaller pieces. If we turn this down to less than 5, this is even smaller pieces, whereas if we start turning this up, you're calling out fewer and fewer pieces the higher you raise this volume. So you can see how this can be really handy when it comes to treating our pieces differently or removing little bits that will, we don't need to compute simulation on these tiny little dots. We can handle these tiny things with particles rather than rigid bodies. So this is a super handy attribute to have at our disposal. We still haven't addressed one of the most important steps of a fracture setup. It's kind of a quick and simple thing, but it's one of the most important, and that is the inside attribute for all of the faces on the inside of the fracture versus the exterior faces here. Most studios have a convention that you'll have a primitive attribute with a value of 1 on the inside and 0 on the outside, and it's typically called inside. The Voronoi fracture node gives us an attribute here, primitive outside, that you can output, but I typically don't use that since an inside attribute is the convention most of the time. But if you look at the groups, we're using an inside and an outside group for the faces, and we can use that to set the attribute however we'd like. So if you middle mouse click, let's do this just below the divide node. If you middle mouse click there, you'll see that we have a number of primitives in both the inside and outside group. So it looks like things are being grouped properly, and we can use that group to set the attribute. Let's use a simple attribute create node, and we'll call this inside and set the class to primitive and the value to 1 with the default of 0. And if we set the group to only set the attribute on the inside faces, that means the inside will get this value, but anything not in this group, namely the outside faces, will get the default of 0. And of course, let's rename this to keep our network clean. Now if we look at the exploded view, there's no visual feedback to show us whether or not the inside attribute is working. Let's take a quick look at the spreadsheet. And you'll see that we do have an inside attribute on the primitives with values of 1 and 0. One small change though, this is 1.0, and most of the time you'll want to just use an integer, not a float, for that value, since it's always just going to be either 0 or 1. So after changing that to integer, you'll notice that the decimal portion of that number goes away. Now let's add some color feedback to not only visualize that the inside attribute is working properly, but also to make things look a little bit nicer in the viewport. Typically, you'll have a different shader on the inside faces versus the outside faces. And just to create a different look on the inside faces, typically it's a bit of a different color tone and texture. We'll just use a slightly darker color on those faces just to make things look nice. So if you drop in a color node after the attribute creation for the inside, let's set the display to the color node so that our exploded view doesn't keep recooking and slowing us down. And you can set the color class to primitive, and the type is going to be a ramp from attribute. And of course our attribute is going to be inside. So what this does is it'll use this color, currently black, where the inside faces are 0, and this color, currently white, where the faces are 1. And of course if we're using a fractional attribute, then it would interpolate in between those. So you can hit this drop down for some more control. And I think it'll look nice if we set the color to white for our outside faces. And let's set our inside faces to mid-gray, maybe about 0.6 would look pretty good. Now let's rename our color node and look at our exploded view. So now you'll see that we're getting a little bit of darkening on those inside faces. We can switch to smooth shaded view, make that a little bit more obvious. It's pretty subtle, but it makes things look quite a bit nicer in the viewport and also verifies that that attribute is working correctly. When you're using this asset to fracture different objects, you might want to look at different steps in the process instead of just looking at the end result and waiting for the end result to cook while you're playing with the different settings. So let's go to our Voronoi Cutters node here, then we'll right click on it and select Type Properties. This will bring us the UI that we were looking at before where we set up our different parameters, and we're just going to add another drop-down box to select what we want to visualize. For this display option, the ordered menu parameter type should work quite well, so you can drag that to the top of your parameters, and let's just call this output. So if you click on the menu tab, this is where we'll set up the different options for the drop-down box. The label column is where you specify the text that's displayed for each option, and the token is the value returned when that option is selected. There are a few different options that come to mind when I think about which things would be the most helpful to visualize while setting up fractures, and those would be all of the Voronoi points, the cutter points alone, the large chunk points alone, and the final fracture. And of course, if there's anything that you find helpful, you can feel free to add more as you see fit. So I'm just going to add all 4 of those options as the text labels. Now for each of these menu options, we'll give it a numerical token that it returns when selected. We can just use values 0 through 3. And these sequential numbers are a good idea to use because we're going to be using a switch statement, and using these values will allow us to use this return value directly in our switch statement without needing to do any extra checks or manipulation. So let's apply and accept that. Now we can right click this output parameter here and we'll copy that and then dive inside the network to set up our final visualization. So at the end of this network, we'll create a null node and simply call it out fracture, because this will be our final fracture here. Now let's create a switch statement and we'll call this viz switch. Now if we right click and paste copied relative references into our select input parameter of the switch, you'll notice this is returning our currently selected option, which is 0. And this will change depending on what we have selected in that drop-down box. Now, here I've created a few null nodes, nicely labeled for our outputs, for large points, all points, and the cutter points. So now I can attach those one by one to our visibility switch here. Now let's zoom in on our switch node here and look at the order of our outputs. These outputs here correspond to a value in the select input parameter. The first one is output when this is a value of 0, and the second for a value of 1, and so on. So let's double check the order in our drop-down box. So we have all points, cutter, large, final. So we know that we set up our tokens for each of these options in that order, so we'll make sure the switch node corresponds to that. Now back in the switch node, we had all as our first, then large, then cutter, then fracture. And now we can set our visibility to this switch node here. You'll see right away that this changes to show us all of the points because that's the option that we had set as the default here. And I think that's a pretty good option. I think whenever you first drop this in a scene and connect some geometry to it, I think the first thing you'll want to see is the points rather than expecting it to cook the fracture first. So if we go through our different outputs, we can check them out to make sure they're working properly. And we'll notice that we made a mistake with the order here because our cutter points is showing us the large points instead. So this is a good example of why it's always good to test these things thoroughly. We just need to rearrange that order and we should be in good shape. So we have all the points, cutter points only, large chunk points, and the final fracture. Now that we're all done setting up our fracture options, we can once again click on this and then click Save Node Type. And if we match current definition, then that'll make sure that this is a copy that reflects the actual saved Houdini digital asset file.